Hello, and welcome back to our third episode of OMG OMx. Our guest today is going to help reveal to you part of how you survived the pandemic, some of the secrets of lipid nanoparticles, and the secrets of his success, because he has learned how to make science work for him. Hey, Michael, thanks for being here today. You're our third guest on the OMG OMx podcast series, and you again have a diverse career background. Can you tell us a little bit about your story and how you got to your current position?
Sure. First, thank you so much for having me, and I do appreciate it, and it's glad to be here. First, my name is Michael. Last name is Girgis, and I was born and raised in Egypt, and then I moved to the U.S. about 15 years ago, and I stayed here in Virginia. I finished my bachelor's degree in pharmaceutical science, and then I got my master's and a PhD at George Mason University in chemistry and biochemistry in 2016, and then moved to Georgetown University for a job in science, basically, and I ended up learning a lot about metabolomics and proteomics over there. And then I moved in 2022, actually last year, to join the Lipid Nanoparticles group here at George Mason University in the Bioengineering Department.
Thank you. Can you maybe describe the focus of your research and what makes it so unique or important? Because this week's topic is liquid nanoparticles, or LNPs.
Sure. LNPs have attracted a lot of attention recently, especially with the pandemic, but it's actually a pretty old topic that people start talking about a long time ago. I would say about 2 decades ago. What we are doing in our group in the Bioengineering Department, what we do is we have synthetic chemists to synthesize the ionizable lipids, which is a big component and a very important component in lipid nanoparticles. And then we have some folks who actually formulate different formulations, different conditions, and we have a few people who are doing quality control, quality assurance, and then we have actually some people doing some animal testing, just to make sure that the formulation was working efficiently and the potencies is about within the specifications, and to see whether the LNP is actually working or not.
Can you explain to us how lipid nanoparticles work and why they're so important in everything that goes on with them?
Absolutely. Lipid nanoparticles really revolutionized the way we think about medicine and the way we had many, many issues before, and now we found some solutions. So what are these lipid nanoparticles? So they are very, very simple. They are small particles. They're nanometer in size. They're self-assembly, believe it or not. They compose so many lipids. Mostly the most important one is the ionizable lipid. They have the core, and then they have the lipid bilayer. They're very simple. They're formed by a very unique and intricate mixing system. Focuses on microfluidics fusion together. And then basically we have a bunch of lipids. The ionizable lipids are very important. We have some helper lipids like DSPC, and then we have cholesterol. And then we have also something called pegylated lipids as well. So we basically mix the lipids in ethanol, and then we have the RNA or whatever in a cargo, because those lipid nanoparticles are basically like cargo for drug delivery system. That's by definition. So we mix those fluids in a very intricate, very, very reproducible way, and then we form these small little particles. It starts off with ionizable lipids, basically positively charged ionizable, usually cationic lipids. They associate with the RNA or DNA, whatever negatively charged species that we put on, and then eventually the helper lipids start coming on to form the first layer, then followed by some other layers. This is the lipid bilayer, and then the pegylated or polyethylene glycolipids basically partition itself, the hydrophobic section inside, and then the hydrophilic section outside, and that helps with the solution. So what makes those lipid nanoparticles very unique is that they solved a lot of problems. Previously, we had some issues with drugs, RNA-based drugs, peptide-based drugs. Those drugs can be hydrolyzed and destroyed by, nucleases or RNases, DNAs in the plasma. So we couldn't actually make it through all the barriers of any the medication had to go through. So with that said, having this cargo that can safely deliver the medication to the cell or through the cellular membrane to the cytoplasm, that was a great achievement. So you'll see a lot of application of this in RNA-based drugs. You'll see some applications in DNA-based drugs. Peptides and proteins can be also encapsulated with limitations because of the nano size. You have a size of 60 to 80 nanometer size. And then we have also some smaller molecules, actually FDA approved of a few drugs actually that can be encapsulated into those small particles and delivered to different organs. That's really the pivotal role of lipid nanoparticles. It's a cargo that can deliver drugs to various parts and through the lipid bilayer of the cellular membrane.
So you started to tell me a little bit that I was thinking a question up on while you were talking. So you've told me a little bit about the real world applications and some of the successes, but you said this is in FDA approval mode, or there are drugs that are being used in this mode?
Oh, absolutely. So talking about encapsulating lipid nanoparticles with messenger RNA, which is very unique and of course saved us from this difficult time in the pandemic with COVID-19. So we have Moderna and Pfizer jumping in with their research, who've been there for more than 2 decades. So basically, we encapsulated messenger RNA into those lipid bilayers or lipid nanoparticles, and eventually we delivered this to various cells. And then, once the RNA is inside the cytoplasm, so the lipid nanoparticles basically inject the RNA with the content through a process called endocytosis. That's what at least believed at this point. And then once what's inside the cytoplasm, the whole process starts, and then you get the protein translation process through the ribosome, and then you start generating proteins. The immune cells start looking at this protein as an awkward protein that we don't really know what it is, and then we start generating memory cells and B cells and T cells to kill this, and this is how you get your immunity. This is a huge success from Moderna and Pfizer, and actually saved this. There are some other very successful examples where we're using short interfering RNA as well. There's a Onpattro. It's a drug. It's actually a commercially available drug where they're manufacturing short interfering RNA inside lipid nanoparticles, and they deliver this to treat certain hereditary disease that comes along, and it's very rare, an orphan disease. So this is an example where we're hacking those lipid nanoparticles with a short interfering RNA, and then we control the gene expression through this process. There are also some examples where we're putting some drugs that are very difficult to be solubilized. They're not water soluble. They're not very friendly. And some of these examples are some of the anti-cancer drugs. Just out of the top of my head, there's a drug that I can remember called Iclusig. Iclusig is actually a commercially available drug to treat leukemia and some other certain types of leukemias and other diseases. So we can actually bypass the solubility issue in a pharmaceutical production, and then we can actually deliver this drug to the places where it needs the most. Also, there are also some drugs where we have a much smaller molecules actually manufactured in lipid nanoparticles, like a drug called Doxy, which is just a regular doxycycline. Doxycycline is very famous drug, like antibiotic you get when you have like some kind of tooth infection or something, just kind of kill bacteria by basically lowering protein expression. What happened is when they start formulating this in some of lipid nanoparticles, it starts actually being very helpful in some kinds of cancer. Um, Another drug that I could think about is called Onivide. Onivide is actually also one of those drugs that I actually used heavily in a solid tumors to deliver anti-cancer medications into these solid tumors. So there is a lot of applications that we can think about using lipid nanoparticles. That's why we're so excited and we're so happy to be part of this revolution in the world of medicine.
I've been a scientist for a few years now, and making it through the pandemic, I'm not sure I heard that good of an explanation of the mRNA delivery until you did this just now. You have a future, I think, in continuing to explain some of these things to the masses.
I really love it. It's really great. Our group is really very active and developing the technology. And George Mason University is one of the pioneers in nanotechnology. And Dr. Mike Page is actually my supervisor. He's really amazing in this, and is like in the Center of Molecular Engineering where I work too. It's just wonderful to work with those people and watch the progress of how we can make the difference and make the change in the world. So yeah, we're so happy, and I'm so proud.
That's fantastic. I mean, these are why I love having these talks and being able to engage with scientists. I can tell that you have extreme passion and tenacity for the work that you do. Can you maybe relay one of your OMG moments as you became a scientist and as you started to become curious?
My biggest OMG moment, which I really love about those podcasts like the OMG, like I call it really an aha moment, more like oh my god moment. But it is very really interesting. So I think the biggest moment that really changed me personally when I really helped and really contributed greatly in identifying an unknown biomarker from exposure to radiation that was really mysterious, and we couldn't really find any matching of this molecule based on the mass spec or mass spec that we obtained. We didn't have any information. It was almost impossible to really figure this out. But I worked for like 2 3 months, and I tried to propose a structure to this based on a fragmentation pattern, and then I basically ended up taking this to my supervisor, and it's like, hey, I mean, this is what I think it is, and if you want to invest a little bit more and try to get a synthetic chemist to synthesize this molecule and prove what I'm saying is right, that would be it. We got a brand new biomarker. So they kind of took my word for it, and then we got it synthesized. And the moment I probably I was almost like skipped heartbeats, like very didn't sleep the night before, worried about it. And then the moment it went through the machine and I see the same fragmentation, same retention time, that's my molecule exactly the same, matching the biological samples. I just feel I'm on top of the world. It's my oh my god moment. I just made it. It's just amazing, and it's actually highlighting how mass spectrometry is so crucial in identification and characterization of various molecules, biological molecules. It helps us a lot really understand a lot about this, about the pathways, about biological entities and what's going on inside the cell steps. Knowledge is power, and this is the power of mass spectrometry.
So, how many types of mass spectrometry have you done over the years? I assume that was GCMS. And how many other experiences have you had with different methodologies?
I've done a lot of LCMS as well, liquid chromatography mass spectrometry. I've done so my education was in basically organic synthesis, like making small molecules. And then when I got some training on mass spectrometry, I started to love it even more and more. I did a lot of metabolomics and proteomics. So got about 23 publications, and it's really a very interesting field, and I'm so honored and proud to be part of this field in mass spectrometry.
So, you have a lot of tools at your disposal and you have a lot of experience with mass spec. So, why is it so critical for LNP characterization? And what is your favorite way that you've characterized LNPs?
Well, this is really a very important question. Very good question, actually. So how is it that mass spec is very important to us? At least LNP folks. Um, First of all, um, it's a self-assembly process. So many things could happen along the way. If the microfluidics are not right, if the buffer is not right, a lot of things could happen. RNA, as robust as it may look, it also can degrade, and we might have some impurities. Therefore, characterization of the starting material is very crucial. And that's why FDA has very strict rules when it gets to impurities and characterizing what these are and knowing what the concentration is. So it's a multi-pronged process. So first of all, we have some starting material that you need to take care of. We have lipids that we synthesize in house. We have lipids that we source from some other companies that we want to make sure they meet the specification of the FDA. We have the mRNA production, which we want to make sure that it has enough purity to qualify for the lipid nanoparticles, because these are going to be intermediates. So we have to worry about this, but the road is not always very, nice and smooth. We have some impurities. Those impurities are very important. Like, we need to know what these are, and we need to know how much they are. So, like for lipids, for example, we see some degradation. Lipids love to degrade eventually. They're very fragile. They hydrolyze because some of these lipids have some ester functionalities, which are easy to hydrolyze eventually. The biggest problem that we have in lipids is oxidation. Lipids are magnets to oxygen. They pick up oxygen from the nitrogen side, they pick up oxygen on the double bond, even on just a CH2 or CH. They pick up very nice oxygen, become oxidized. $1 million question is, where is the oxidation happening? Is it on the tail end of the lipids? Is it on a connecting portion of the lipid? Is it on the head, which is so crucial during the formulation, the cationic head of this lipid? So understanding all of this is going to help us make the right decision about whether or not these starting materials qualify for this. Once we have the formulation, we're not done yet. Once we formulate your LNPs, now we have another question. So what happens if we leave this LNP or this vaccine on a table at room temperature for a couple of hours? So would this be detrimental to the efficacy and potency? So we have to study stability, storage conditions. It's a big deal. We had a massive issue when we had Pfizer got approved, like back in late 2020, when we have to store it in negative 80, but not negative 80 degrees Celsius refrigerators, and we don't have those all over the place. Of course, we figured it out, but it was a big deal. It's like, how do I make my formulation very stable? And what happened if this doesn't exist? That we don't have these conditions in African countries where it's super hot. We don't have the refrigerators. So we study the degradation product. We actually model the degradation, and we call it forced degradation studies. So we work on this from the lipid side, starting material, from the formulation side after we're all said and done, and for the RNA. So we have to study all of this. We screen for everything. We want to make sure the sequence was right. We want to make sure that the starting material was right. We want to make sure that even after the formulation is done, the conditions of the formulation didn't impact the components that we have. So this is all the quality control and quality assurance. And this is as simple as it could be, but it's really it's a very important aspect of lipid nanoparticles. And this is where we need a whole lot of capable instrumentation to be able to answer our questions, because not every instrument can answer these questions.
Thank you so much. That was, again, a really clear-cut way of explaining this. I just want to keep talking to you more and more and more on all of this. So something else that kind of came to mind here, you've been talking about the tools that go into the work that you do, but tools can be more than just instruments. So what about the people, the support, the collaborations that you utilize and that have helped you to be successful here?
So one of the things that actually helped us a lot to be successful, got us where we are now, is how we communicate together. We meet on a regular basis. We talk to each other, and we have some open channels a lot just within our group. Now, talking about collaboration, which is really very crucial here, because not every person is an expert in everything. It's like you're going to be an expert in one aspect, but you're not going to know everything. So that's why we have lines of communications with a lot of collaborators all over for lipid nanoparticles specifically. So, for example, I have Dr. Dan Fabris from University of Connecticut actually helping us a lot do a lot of method development in using mass spec in characterizing messenger RNA. He has a wonderful team of people. Just remember Daniele and Tom, who were actually working with me, running samples and acquiring, on the instruments and teaching me how to do a whole lot. And I was visiting them a few weeks ago. So also, I would say that having some partnership with the industry, like our collaboration with Bruker Scientific, really helped us a lot, kind of develop this and advance more because it gave us the capabilities that we didn't have. I just want to mention that there are a lot that Bruker Scientific and some industrial partners can actually provide that we really don't have in academia. And I would say like Erica Forsberg and Matt Albano was really very supportive along the way. And I can't really imagine making that much progress in characterizing lipids and degradation products without them kind of jumping in and helping and supporting in the whole process.
So to maybe transition a little bit on how science works for you, because I think we're getting to that point where you're telling us how you've gotten to the point you're at in your research. So you've had a lot of different career experiences. You've worked a lot of different places. Have you always been able to channel your passion for science, no matter the job or the question? Is it just mass spec? Is it anything science? Tell us a little more about how you stay curious.
I think after I finished my bachelor's degree, I think we got together in the graduation party, and then I got some of my colleagues asking this question, and so it's like, "What are you going to do next?" And then I said, like, um, "I don't believe this is the end. I feel like this is just the beginning. Like, there's a lot more that I need to be doing." So throughout the years, I joined the patent office where I started to be more and more curious. I worked as a patent examiner for 3 years, and that really got me so interested in science. And I started kind of, slowly deciding that this is what I want to do. And I started, thinking about science. And in the patent office, you learn a lot about the laws and the rules and regulations, and you learn a lot about how to write that piece of art. It's not just it's not just you're writing a written opinion, talking to the applicant. It's more like you're writing a convincing argument, more than just writing a response. So that really got me into it's like this is how science should be. I need to convince you through my words that this is the way it is, and my words have to be based on facts. And I found a lot of passion to this because I love to write, and that helped me a lot along the way. Moving forward to my master's PhD, you write a lot of proposals and you write your defense, and that's like my dissertation was like 500 pages long, lots of stuff. And then moving to writing papers, and then writing proposals and grants, and that. So I find this passion everywhere I go. However, I also still need to kind of jump in the lab on a bench and start kind of doing something by my hand a little bit more. So it's been always really, it's been always the desire of my heart to do something in science that nobody else could do, and I wanted to do this really eagerly. And I'm so grateful to the opportunities that I had in my life.
As a PI, you're telling me that you still go into the bench, you still sit in front of the instrument, and you make time for this in your daily rigmarole. That's impressive. Tell me a little bit more about why you stay so connected in the lab and with the instrumentation.
First of all, there's a lot more to learn about instruments. So it's not just like, yeah, I know it all. Like, it's like, no, it doesn't work this way. So I love to work on the instrument. I like to work on a problem by myself. And this is really what got me into science, that I see a problem and I work on it. And I try to focus and filter everything else outside of my focus on my brain. And then I try to focus on this. One of the things that I love to do by myself sometimes is that when I train some of my students, graduate students or undergraduate students, I love to sit with them and go over the principles, go over the concept first. And then I teach them all the ins and outs. It's like, you got to be careful how to do this. If we don't start from the younger generation and teach them exactly how things are, they're not going to grow as future scientists. Eventually, we're not staying here forever. And we have to pass on this knowledge to other people. And the younger generation is really a good soil and good material that you can actually grow in and inflame science passion in them. And these are the people who are going to be future leaders and future scientists. I remember one of my students, Rachel Harden. She walked in. She wasn't really interested in chemistry, and one time she came to me and she said, "I would like to work in a lab with you. And maybe I want to see what you're doing." She volunteered in the lab for almost a year, and I'm going to tell you, Rachel has now got a PhD in organic chemistry, and she is a big patent examiner in the United States Patent and Trademark Office with a PhD in chemistry. So, and she was a biology major. So, things like that would make me like I have a scientist in me. I need a scientist. They have a lot of passion, and this is just the case with all my students. I love to work hands-on, teach and go over the principles with them, because they're not going to find this in any textbook. The troubleshooting of the instrument, tuning the instrument to get what you need out of this instrument, doesn't really matter how fancy or advanced you are. But if you really know the principles, you can get through it and you can get the best out of what you have.
I can tell that academia is sitting really well with you. And I think for you to hold on to that, your optimism is absolutely coming through. And I really admire your commitment, Michael. But I have one last question for you today. So, how far would you go to fund yourself and to keep your science going? Would you live a minimalist existence in a treehouse? You could go out into the Virginia woods. You hope to win the lottery and you could take that money and funnel it back into your science. What do you think? What would you be willing to do to make sure that you can continue doing science?
Well, winning a lottery is always an option, but if you can do it, good luck with that. So it's really a very interesting question. So, what are we going to do around this? A part of nature, my nature, is to love to compete, and this is where academia fits a little bit better for me. I like to compete. I like to like convincing arguments with others. So, winning a lottery, having some funding from this, that would be great if we have it. Well, if we don't have it, I would say I'll keep doing what I'm doing. I'll keep trying to propose something here and there. Don't get me wrong, industry is really a very good field to be in. And that's why you see a whole lot of influx of people moving from academia to industry. Part of it because of the inherent problem that we have in industry, by the way, that industry doesn't have well-qualified trained personnel, and they don't have the time or the resources to train somebody from scratch. So that's why they would prefer to get a trained academic person to take over, for example, mass spectrometry or a very well advanced mass spectrometer. So they prefer this. However, in academia, you get to learn along the way because you do have time to learn and develop your skills. You don't have that much time in industry. So that's why, you get a whole lot of people going from academia to industry. Now, is industry great? Yeah, for sure. It's because of industry we've been through the pandemic and a bunch of other diseases. So we owe the industry a lot. But academia, on the other hand, seems to be more relaxed. They got more time. They don't have as many resources. But if we have the resources, life will be a lot easier.
Thank you so much, Michael. I really have enjoyed talking with you today, and I'm so grateful that you made the time to share your experiences and give us some of your wisdom, which is really good.
One of the things that I like to tell my students when there are so many days when you walk out and you have this moment of, you're desperate, you're just kind of tired and it's nothing is working. So I always tell my student this, no matter how bad things are, you can always make it better. No matter how bad it is, tomorrow's going to be better. You can always make it better on yourself, on the surrounding, your environment, your family, your coworker, your colleagues. So don't give up. You're going to always make it better, no matter how bad this is. So,
I think your colleagues, your students, and all of the people that you work with are really lucky to have you. And thanks once again for being with us today.
thank you so much. I really am so grateful. And thanks for having me. It's such a great honor. Thanks a lot.
Michael gave us such a great summary of all of the work that he does and all of his collaboration. But I think once again, we need to help him a little bit. So, what do you think he should do for a competition to earn some extra money to make sure that his science keeps going? I'll put a few comments in the comment section below, and maybe you guys can like them, vote them, and get us going. Hot dog eating competition? Axe throwing? We'll come up with something for him.